Welcome back. We're going to continue on our discussion of physical optics. Which will give us some powerful tools to reintroduce some of the wave behaviors like diffraction that we observed in geometrical optics, or did not observe, actually, when we covered that. So here's a review of what we've left off with. We've got a point source. This is at the vector r, naught. What we want to do is figure out how does that point source influence radiation at an arbitrary point, r vector. And our problem is that we have this intermediate screen that blocks radiation here, except for this aperture A. So we'll need a little r prime vector that will serve as our variable of integration, and we're going to use sort of the grown-up version of Huygens principle. We're going to add up all the contributions along this aperture of the illuminated field that it makes at that point. Now to do this, we have to invoke Kirchhoff boundary conditions, which says that this total field on the surface is going to be just the illuminated field, and that the boundary here is perfectly blocking. There's zero field anywhere around that aperture A. We discussed why those are approximations last time, and this was our final result. We take that field, average it around, or add up all the contributions through integration, integrating over x and y, with this phase term and this amplitude weighting based on whatever initial field came from that point source. Now, we're going to make an approximation here in this lecture, and I wanted to dedicate a lecture specifically to this because this is one of the most important aspects of electromagnetics. We're then going to apply this approximation to various terms or various problems. Rectangular aperture, which we will get a result for the finite rectangular aperture, and then we will allow the size of that rectangular aperture to stretch to infinity in two directions along the width and one direction along the top, and that will magically give us a half plane. What we do with that half plane then is figure out what the diffracting fields are, and this leads to one of the key results in electromagnetics called knife edge diffraction. It's a very practical formula. It has a lot of applications in designing everything from a point-to-point microwave link to optical diffraction at the nanoscale. So we're going to build that formula. That's ultimately where we're heading. And then once we study the half-plane formula using knife-edge diffraction theory and the Kirchhoff-Helmholtz integral theorem, we're going to change gears, and we're going to look at it from an exact field perspective, because the knife-edge problem, where you have a perfect electric conductor that shields radiation, actually does have an exact electromagnetic solution, unlike most canonical problems in electromagnetics. And we can kind of compare and contrast how does the Sommerfeld solution involving perpendicular and parallel polarization stack up to the Kirchhoff-Helmholtz integral theorem analysis that we've introduced here. What does that diffraction look like? And it'll turn out that that solution will in turn give us a really nice way to correct the geometrical optics solution that we started out the class with, because it leads very naturally into the geometrical theory of diffraction, which then can be built upon a little bit more to give you the unified theory of diffraction, which then gives us an idea of how to correct and add to the solution of physical optics to give us the physical theory of diffraction. And so we have kind of two parallel tracks that, of course, are solving the same problems, but each has different applicabilities and different strengths and different weaknesses, different trade-offs. We have physical optics and our geometrical optics. And since they describe the same phenomenon, they need to be harmonious, and we'll be showing how that's true along the way. But let's look at this issue here first of all. If I go back to my first slide here, I have distances. And making approximations is really, in evaluating these, is really about replacing these complicated vector distances. I'm taking the magnitude of a vector that's going to be slid around. Remember this r prime. I'm sliding that around my aperture, picking up all these integrated contributions. I want to be able to approximate that with something similar, because these geometric terms are very difficult to work with in integration. What I can approximate them as depends on where they are in this expression. Generally speaking, your amplitudes are pretty easy to approximate because they don't change much. In other words, the distance from the point source to, let's say, the origin, which we hope is kind of close to the center of the problem, x, y, z, here, that origin point, the distance from here to here, let's call that just scalar r naught. Well, if I move over here and I try to pick up a contribution from that point to the source, chances are either that distance or some other distance is going to be pretty close to r naught. And because it's in the amplitude, it doesn't really change it if I'm a little bit off. In fact, presumably I'm going to be a little bit off in one direction on this side, a little bit off in one direction on that side, and it won't make too much of a difference. Some of these errors in amplitude will actually cancel each other out as I integrate over all the distances. And the same is true for okay, so the other place that we have to make an approximation is in this part right here. That area is a lot more sensitive because we're talking about phase. It's not really the total distance that matters, it's the modulus 2 pi phase inside the complex exponential. So that tends to be a lot more sensitive to approximation. We have to figure out how to deal with that. So we actually have a couple different ways to deal with this. Ultimately, we write this as the square root of the square of the sum of the differences between the point on the surface and the point of observation. And we should also note that the same is true for r naught minus r prime. I'm just putting x naught and y naught and z naught into here instead of the point of observation coordinates. And I can write this basically as r, the distance between what is approximately the center, if we've placed the origin at the center of the aperture A, and whatever observation point or source point that I make. So the distance between, what's roughly the middle of the aperture to the point of observation, we'll call that r. And then this distance here we'll call r naught. That's from the source to roughly the center of the aperture. So if I do that for r minus r prime magnitude, I can write that as an amplitude term, r, because basically what I'm saying is that when I factor this out, r is so big, my point of observation is so far away, that these minor displacements in x prime and y prime don't really amount to anything. And that's the approximation that I use in the amplitude. That one right there. There's another correction here, which is basically the direction r hat that points to the point of observation dotted into whatever vector r prime I'm integrating around this aperture. And what I'm doing there, by projecting it in that direction, I'm making an adjustment for whatever displacement happens relative to the origin. And I'll show that a little bit more clear in the graph on the other page. And then there's a higher order correction factor, which we call this the Fresnel term in phase. It's meant to account for the small area deviations as I move around here. The fact that this line does not stay parallel when r, my point of observation, is drawn in somewhat close to the aperture. Now, this may look like very sophisticated stuff, but in a way it's just sort of the 3D equivalent of doing a Taylor series. We've factored this out in a way so that we have basically 1 plus a small term. And if I were to take any type of mathematical function that's the square root of 1 plus a small term, I get a dominant term that's 1. That's my amplitude term. My Fraunhofer term is like the linear correction to that, w over 2. And you can think of the Fresnel term as simply the w squared over 8 follow-up correction factor for this. That doesn't mean that there aren't other terms that I could add in to make this even more precise. But generally, when I'm very far from the antenna and just looking at amplitudes, that's what I need. Or when I'm very far from the radiating aperture. When I'm very far from the radiating aperture and I want to take into account phase effects, that's the term I like. And if I want a better correction factor, that's the term I'm after. Graphically, we can relate this as the following. Here's our aperture. Here's our point of observation. What we're saying, if we make the approximation in amplitude r, is that no matter where you are on the aperture, the distance from there to the point of observation is always the same. So that's clearly not the case for this point that I've designated very far or very close to the aperture. But of course, if I was way over here, that wouldn't necessarily be a bad approximation, especially in amplitude. For phase, the Fraunhofer approximation, we add this correction factor to it. And here, we're projecting the difference. So if I were to take this line that's perpendicular to the direction of propagation from this aperture, and I translate it down to the origin, this little projection factor is telling me how much closer or farther away a point is on the aperture if I draw a parallel line to that same point. Now that is not a bad approximation, and it gets very accurate once you get an appreciable distance away from the radiating aperture. However, when you draw in close, you see that that parallel line is not going to be exactly the same distance as that line that goes straight to the point of observation. And this line here that I've drawn parallel is not exactly the same distance as this. And when you are up close, that can make the difference between 45 degrees of phase change or 90 degrees of phase change, or sometimes even more, turning something that in the far field looks like it's constructive interference to destructive interference in the near field. And so the Fresnel approximation has all three terms for distance that we add into phase. And is a much better representation of exactly that distance. It's still an approximation. It's not the exact distance here, but it's pretty close. And it works very well unless you're like right up on the aperture surface. So those are the key areas, the key approximations we're going to make. So this is what we're going to wind up doing. Here's my distance from aperture to point of observation. Here's my distance from aperture to source. If I make those approximations according to our formulas on the previous page, this is what I get. And keeping in mind that r hat is the direction from the origin to the point of observation, and I can write it out in spherical coordinates and unit vectors x, y, z. And I have the exact same formula for my source. So if I use those formula, I get this expression. I can plug it in. And here is the full-on Fresnel approximation with all of our approximating terms for both distances. And it is quite complicated. So we're going to make one mathematically simplifying assumption. I'm going to line things up here so that the origin, the source point, and the observation are all collinear and lie on the xz plane. And this is pretty easy to do. There's not too much loss of generality here because if you're allowed to shift the origin to wherever you want on the aperture, this is sort of the cutaway of an aperture. If I had a circle over here and a point of observation and a source point here, I would just place the origin here knowing that my actual aperture would be translated a little bit away from that point. Okay, so let's see what that buys us. All those ugly expressions with the Fresnel approximation simplify to this. Much simpler. And the angle that this is referring to is the angle that this makes here between the z-axis and that line that points from source to observation. So if we do that, and we basically throw away all but the first term whenever we're doing amplitudes, the KHIT expression simplifies to this beautiful result here, where I have, when I factor things out, a really nice intuitive expression. It's going to depend on the amplitude. There's going to be fall off with respect to the distance from source to aperture and from aperture to point of observation. There's going to be a phase term, and the dominant phase behavior is going to be just the sum of the distances traveled. There's going to be an adjustment in the amplitude and phase made by this integral, which you integrate over the entire aperture A, adding in these phase factors and the Fresnel adjustments as the variable of integration slides around whatever aperture you're integrating over. And this way you can figure out what happens when a point source illuminates an aperture, which then re-radiates to some other point on the other side. And you can get both of these points fairly close to the aperture and still see some of the effects. Now at some point, you start to really approximate either the Kirchhoff boundary conditions fail, or even this phase term fails to capture what's really going on. But surprisingly how close you can bring those together and still have this work. And so in our next lecture, we'll talk about some specific instances of applying to this to some various apertures. And ultimately, we'll want to get into the knife edge diffraction problem, which uses the KHIT formulation. Now, one other comment. If we have a flat surface and we illuminate it with a wave, either from a point source or a plane wave, which would just be a very distant point source. Let's say this is metal. We have an incident wave, and we're going to have a scattered field solution. And the two of these, when they add up, if they're the tangential components of E field, should add up to 0 on a metal. And it's the scattered field that in the geometrical optics solution made a bunch of rays that were modeled as angle of incidence equal to angle of reflection. Well, now we actually have another tool in our arsenal where we can take that scattered field, plug it into the Kirchhoff-Helmholtz integral theorem, evaluate it with Fresnel terms if necessary, and get the actual field coming out of here. And unlike the geometrical optics field, there'll be some diffraction effects and some far field beam forming type of effects. It's not just going to be a collimated artificial solution all the way to infinity like optics would predict. So this gets us a little bit closer to understanding diffraction formulas and phenomenon, and is another really powerful tool in our arsenal. So we'll go ahead and apply this to some problems in the next lecture.